So the network layer is pretty much where the majority of a network technician, network administrator, somebody that's doing the infrastructure part of networking, and a cybersecurity person is going to deal with. Occasionally, you may need to delve into the lower layer, data link layer, but most like, let's say, cybersecurity attacks are perpetrated at the network layer and above. Could be application layer as well. Actually, application layer is pretty common layer for cybersecurity attacks, but a lot of attacks focus on the network layer. And so your understanding of how it works and being able to look at packets and understand what's in them, or at least be able to understand what Wireshark is telling you is something that'll be helpful. And of course, IP addressing is part of that. And our friend subnetting is part of IP addressing. So our first labs that involve subnetting are next week with module 11 labs, where part of the lab, the first part of the lab is creating a VLSM, variable length subnet mask scheme for a particular topology. But anyway, we're not going to get into subnetting in this module. We're just going to talk about the role of the network layer. So it provides logical addressing for end devices. And when we say logical addressing versus physical addressing, it's because IP addresses change frequently and can easily be changed, just by going in and, into a dialog box and typing in a new address or requesting a new address from DHCP in some instances. So they're a logical address, whereas of course the MAC addresses are physical address and they don't change, at least not very often. They're not intended to change. And I have not shared my screen. Somebody in Zoom land should yell at me when I don't do that. Okay, I did just now, so sorry about that. All right, so addressing end devices, routing, de-encapsulation, encapsulation and de-encapsulation. And it encapsulates the segment as it travels down from the upper layers. So a segment becomes a packet, and then it de-encapsulates going up the stack. When receiving data, it takes the packet, does what it's supposed to do with that packet, and then strips the header and it becomes a segment again before being sent up the stack to the transport layer. Okay, another thing, as far as the two sets of addresses, another way to look at MAC address versus IP address, physical address versus logical address. It is the MAC address, and let me put it the other way. It's the IP address that gets the packet to the destination network. It might be the same network, in which case the IP address is, in a sense, not even important. It's the same network. Mostly the MAC address is what's important when the sender and receiver are on the same physical, let's say, broadcast domain. But when the sender and receiver are on different broadcast domains, different networks, different subnets, then the IP address gets the packet to the network where it's supposed to be delivered. The MAC address actually is what's used to deliver it to the end device. Now, that doesn't mean that the IP address doesn't play a role in the end device. It is essentially like a verification. You know, if it's read in by the NIC and sent up the stack, sent up the layers, then assume that means that the MAC address was correct for the end device. It matched the NIC on the end station, or it was a broadcast. Once it gets read in by the NIC and sent up the layers, the network layer really just verifies. You know, it's like, okay, is this really supposed to be for me? It's kind of like when you move, right? You move into a new house for weeks, months, sometimes. We've been in a house for 11 years and 2 previous owners, which has to go back 20 years, we're still getting their mail, 20 years. But anyway, so the physical address on the envelope is what the mailman goes by and put it in my mailbox. And when we get it, you know, before we open it, we might open it anyway for this person, since we know it's 20 years old or more than 20 years. It's a verification. Is this really the right person that's supposed to open this? So that's another way to look at the IP address once it's delivered to the end station. It's sort of just a verification. It can happen, doesn't happen often, but it can happen that a frame gets delivered to an end device and it turns out the IP address is incorrect. And what happens, the network layer just tosses it out. Said, well, it got here, but it's not for me. And that can happen most frequently with when the ARP table is out of sync. Somebody just changed their IP address and the ARP tables are still showing, you know, that this IP address belongs to this MAC address, and now that they're out of sync. It won't happen. It won't happen for very long, or at least it shouldn't, because ARP tables are aged out fairly quickly in most operating systems. They tend to stick around a little bit longer with routers, since routers are, you know, are delivering so many packets that they tend to keep the ARP cache a little bit longer than end devices do. So it'll eventually get straightened out, but it can happen that a packet gets delivered based on the MAC address and the IP address is wrong, but just not very often. So that's why it's a verification. So getting the packet to the right network, which is of course where routing comes in, is let's say the key purpose of the IP address. Once it gets there, the MAC address is necessary to deliver it, and the host part of the IP address is just a verification. Okay, so I think there's not much here other than they're saying that IPv4 or IPv6 can be the packet header, and it doesn't change anything about what's inside. In other words, there isn't a TCP v6, right? There was no need to rewrite TCP, the transport control protocol, which is at the transport layer, or UDP for that matter, just because IPv4 was changed to IPv6. That's one of the nice things about layering your architecture, so that you can make a major change to one layer and it doesn't have to affect any of the other layers. Now, I will say that there are some, any upper layers that deal specifically with IP addresses as part of their upper layer function. For example, DHCP. I mean, that's its job, is to deliver IP addresses. It's an application layer protocol. So yes, DHCP had to be altered in order to accommodate IPv6 because now it's dealing with 128-bit IP addresses instead of 32-bit IP addresses. And there's other complexities with DHCP with regard to IPv6. And then DNS is another one. DNS, maps host names to IP addresses. And now, again, it's storing an IP address that's 128 bits versus 32. So DNS is an application layer and had to be modified to accommodate IPv6. And really, but all it really had to be done there is allow for a bigger address. There isn't a DNS v6, in other words. So the same process for doing a DNS lookup, that doesn't change. Okay, so DNS was just really minorly changed to accommodate v6. DHCP had to be radically changed because that's its whole job is to deal with IP address. DNS really just made a bigger space for storing the IP address. And the same space stores v4 or v6 addresses. And they had to add a new type, DNS record type, the quad A, the AAAA record. Anyway, so, this is saying that, as you know, each hop between routers, the data link layer addresses change because, we're delivering frame from router to router. So you've got to change those data link layer addresses so that the router will actually read it. IP addresses throughout the whole journey between source and destination, no matter how many routers it has to go through, the IP address in most instances does not change at all. It just stays whatever the source and whatever the destination. Of course, in reality, we know that network address translation, does alter that, but it's only usually in one place, one router, and that's the gateway to the internet, that whatever the network is, whatever router connects the internet will usually do the NAT. But other than after that, there's no additional changes to the IP header, the network layer header. Okay, and the thing is that's one of the many reasons why IPv6 came about. The biggest reason was what? What was the biggest reason that, or at least let's say the most pressing reason for IPv6 versus IPv4? Yeah, address space, right? 32 bits gives you 4 billion. And so all you got to know is there's 8 billion people in the world, and almost everybody has a damn phone. So if your phones are getting a IP address, a public IP address, then just the number of phones in the world alone would probably take care of the entire 32-bit address space. And as you know, there's a whole bunch of addresses you can't even use, right? First off, we only go up to 224, 223 in the first octet. So we've wasted, 224 through 255 in the first octet, which is, a bunch of addresses, 24 bits times another, whatever that 224 to 255 is going to end up being. Another 5 bits. Yeah, so 29 bits of addressing that we've wasted just because of multicast and experimental class E, whatever those are. And then there's the the other reserved addresses, you can't use 0, you can't use 127. You can't use the network ID, you can't use the broadcast ID for, assigning to a host. And then you got all the private addresses that are reserved. So, that 32-bit address space is even smaller than 4 billion addresses in terms of addressing devices out on the internet. So yeah, address space was a big one. IPv6 gives us 128 bits of address, which is just an astronomical number that in all, most people will say, well, they never thought they'd run out of 32-bit, but if they went to just 64 bits, you might have an argument that, well, it's, maybe you could still run out of addresses. 64 bits is still huge. I don't even know what it is. It's that big. You take 4 billion, double it 32 times, and that's what 64 bits is. That's a lot. But it's 128, which is, you take whatever that is and double that 64 more times, and that's what 128 bits will give you. So we're not going to run out of IPv6 addresses. So the other thing, though, is IPv4, you have to go through all kinds of gyrations to do things that the modern internet requires. So NAT was one of the first things. You wanted people to, you didn't want to have every computer inside a private organization and behind a private network have a public IP address. First off, we would run out of IP addresses decades ago if that were the case, if NAT didn't come along. But the other problem with NAT, if you didn't use NAT, if everybody's device inside a private corporate network was using a public internet address, everybody's device would be much, much more vulnerable to the outside world. In IPv4 was built without any thoughts too much of security. Security is an afterthought. With V4, you have to do, additional encapsulations and so forth to get encryption, to get your packets encrypted. IPv6 really accounts for all the shortcomings of IPv4, not just address space, but there is no IPv6 NAT. There's no need for it. There's no, our security is built in to IPv6. You don't have as big a problem with things like broadcasts with IPv6 because there's no such thing as a broadcast with IPv6. So there's a lot of reasons it was developed, but lack of address space was the biggest reason. And we will be talking more about V6 by module 10, maybe it's 11. In any case, so what does it mean to say that a protocol, internet protocol is connectionless and best effort? They kind of go hand in hand, connectionless and best effort. Yeah.
Well, so there's no handshake.
Mm-hmm.
The best effort means I sent it, you do what you want with it. I don't care anymore.
That's exactly right. So connectionless means there's no need to establish a connection before you start sending data. Again, you can look at, I use the two-way radio analogy because it works for this too. Connectionless is the two-way radio. You press the button and start talking and you don't know if somebody's listening or not. Okay, you think there's somebody out there with another radio that might be listening, but you don't know for sure. They could be talking to someone else and not hear you. So that's connectionless. Whereas connection-oriented is telephone call. You don't start talking until somebody picks up and says hello. You know, because the phone rings, you hear it, the person hears it, says answer, and you hear them answer, and now you know you can have a conversation. So IP doesn't do any of that. It's two-way radio. You know, it just sends. And like you said, best effort means, you know, hope it gets there. It's not my job if it doesn't, to fix it if it doesn't.
It's like no guarantee, right?
No guarantee, right? There's no return receipt or anything like that with IP. It just sends as fast as it can. And the only way that you know an IP packet was received is if you get an appropriate response. If the protocol that you're using requires a response. So ping, for example, ICMP, it's basically ICMP can be looked at as an additional layer above IP or inside IP. But the ping protocol, ICMP, it expects a reply. And the ping program actually expects a reply. ICMP is connectionless and best effort. So it's the application layer, which is, in this case, the ping program is the best you can do in terms of saying there's an application layer, because there really isn't. With ping, there's just a network layer, but there's a user program then that is responsible for deciding, okay, did we get a reply or not? So when you run ping, it basically, you know, registers itself with the IP stack and says, you know, if you get a reply from this address, send it to me, you know, to the ping program. If no reply is received, then ping, you know, waits for a while and then says, oh, I didn't get anything, so timeout. Every once in a while, you'll actually get a reply, but ping is already timed out and doesn't know that there's a reply. It just, you know, it doesn't wait. After its timeout period, it says, oh, it's not coming, and moves on to the next packet if there is a next packet. And media independent simply means it'll work with any lower layer protocols. Any, you know, data link plus physical layer makes up the media. And so it'll work with Ethernet, with twisted pair, 10 megabit, 100 megabit. It'll work with 10 megabit coaxial cable. It'll work with ArcNet, 2 megabit ArcNet. It'll work with token ring. It'll work with, you know, Wi-Fi, of course. So that's what media independent means. It basically says, as long as the data link layer and that MAC and, well, the LLC sublayer does what it's supposed to do to communicate with me being IP, then I don't care what those lower two layers are. They could be a serial port. Literally, they could be a COM port going at 9,600 bits per second. IP doesn't care. Now, at that speed, it might care for things like timeouts and stuff because it doesn't expect things to be quite that slow. But for the most part, it doesn't care what the media is. Okay, so we pretty much talked about connectionless. The other analogy for it is good old just drop your mail in the mailbox, USPS versus a registered letter, right? You pay more for a registered letter. That means, let's say because there's more overhead for the USPS to handle registered letters. Registered letter means that they got to get a signature from the recipient. And then that's, you know, an acknowledgement. Well, IP is just plain old USPS. Registered letter is more like TCP running on top of IP. TCP does the, you know, verification, the acknowledgement that something was delivered. Okay. Best effort, think we pretty much covered that. There's no acknowledgements in IP. No error, the only error checking is the checksum in the packet header. And that really is just a check of the, the data inside the packet header. So, very low overhead, which is why, IP is fast, because it doesn't have to do a bunch of extra stuff. Just basically put the encapsulation on there and send it down to the lower layers. It's good. That's its job. That's all it has to do. Okay, so, the term unreliable sounds bad, and in a lot of areas, it's been, the term has been removed from the literature. They're used, what are the two transport layers in the TCP/IP stack? What are the two transport layer protocols? TCP and UDP, right? UDP, the original name of UDP was Unreliable Datagram Protocol. Well, that just didn't sound very good. So they changed it to user, which doesn't make any sense. User Datagram Protocol makes no sense at all, because a user is further away from anything that runs UDP than anything else. So it used to be, Unreliable Datagram Protocol. But IP is, unreliable in the sense that there's no fixing of problems. If packets don't arrive, if they get dropped, if there's errors in them, they get tossed, and no automatic resend or no indication to the sender that there's a problem. That's why you have the upper layers, is to take care of situations like that. All right, we talked about media independence. So one of the things that has to be communicated from the lower layers to the network layer, and actually and above to the transport layer, is the MTU, the maximum transmission unit. And that's because IP doesn't want to fragment packets. It doesn't want to get a big, 2,000 byte datagram from the transport layer and have to split it up to go across Ethernet, which only allows 1,518 bytes. So one of the jobs of the lower layers, the data link layer, and probably the LLC part of the LLC and MAC layer sublayers, is to communicate what the MTU is of the underlying media, maximum transmission unit. And that way, mostly the transport layer knows how big of a segment can I send down to IP, to the network layer, so that it doesn't have to fragment the packets. Because fragmented IP packets, as I mentioned before, is not good. Like it says, it causes latency, but the other thing is, if packets arrive out of order, they can't be put back in the right order if the fragments arrive out of order. So there's no, rearranging things if it's a packet, if things are fragmented. Fragmentation, if you want to call it that, or let's call it segmentation, is the job of the transport layer, and it handles that. Okay, there is no such thing as fragmenting in IPv6. So if it's, if the transport layer sends it too big, then it's not going to get sent, period. It's not going to work over IPv6. So that, is something that you don't have to really worry too much about. I haven't really tried it, but with ping, the ping program, besides just ping and an IP address, there's a whole bunch of options that you can select. You can select how many pings you want to send, But you can also say, how big of a packet do you want to send? And so you can basically, see this whole IPv4 fragmentation. There's a bit in the header of IPv4 called DF, do not fragment. And you can make ping, send it, tell it that you want packets that are bigger than 1,500 bytes, basically, which would cause fragmentation. Well, say bigger than 1,518 bytes. And tell it, do not fragment, and IP will, come back and say, packet needs to be fragmented and the do not fragment bit is set, so I can't send this. Well, I haven't tried it with IPv6, but I suspect the same thing, although you don't have to tell it, don't fragment, because it can't fragment. So if you tried to send a extra large ping packet with V6, it would probably just tell you it's too big for the media. So anyway, that's the purpose of the MTU, is to communicate that up to the transport layer, so that the transport layer will create segments of appropriate size so that no fragmentation is necessary to deliver it on the media. So I believe that size on standard Ethernet is 1,460 bytes. So once you add the transport layer header and the network layer header and the frame header, that adds up to 1,518 bytes. If you take that 1416 and then add another 58 bytes to it. Okay, so if your MTU is smaller than that, which in the days of internet connections via modem, your MTU of modem connections was somewhere on the order of 400 and something bytes. So, if for some reason, if you were basically going from an Ethernet network to a modem to go out to the internet, packets were going to be most likely fragmented unless there was some gateway in between that handled, basically put a new transport layer header on there. And that's why, transferring large files over modem via IP was a disaster, because if one packet's missing, since they're fragmented, you can't, with TCP, that fragment is missing. There's no way to recover it. And so you'd have to restart the whole file transfer again. All right, so let's look at the packet header. So a lot of stuff in the IPv4 packet header. You'll see that with IPv6, they've gotten rid of some of the complexity of the header. And that a lot of it is just like this fragment stuff that and these flags. So a lot of these things were removed in IPv6 or replaced with something else. But there's fewer fields in IPv6 packet headers, as we'll see. So of course, mostly what we care about is this guy. TTL comes into play in certain things like trace route, but usually, you don't have to worry about the TTL too much. Although the TTL can sometimes give you at least a hint, since the two most common operating systems out there are Windows and Linux, and they both tend to use different TTLs in their when they send a ping packet. You can, basically based on the TTL received by some remote device, get an inkling whether it's a Windows machine or a Linux machine, just from the TTL alone. But other than that, you don't need to worry about it too much. Anyone know why is there a TTL, a time to live, in the header of a packet?
So it doesn't just bounce around on the internet forever?
Exactly. So you could get a situation, and not just the internet, it actually, I think, unless they fixed it, I might even be able to make it happen here. If you send a packet out with an IP address that is, let's say, the network, the classful network, or at least part of the network ID exists out there, but maybe the particular subnet that the addresses belongs to doesn't exist, then you can get a situation where routers just kind of, they pass them along to each other because they think each other is supposed to know how to get the packet to its destination. One of the things that happened when we did a big subnetting of our network was, we got a situation where a packet would go out addressed to a particular subnet of the 172.231 network. And that subnet didn't exist. Okay, it was, a subnet we never used and didn't have an actual segment that was assigned that subnet. So what routers do is when they can't find a network in their routing table is they usually have a default route that says, okay, if I can't find it in my table, it goes out here. So my router would take, let's say, a packet addressed to 172.31. Let me think of an address that wasn't in use, or a subnet that wasn't in use. Let's just say 172.31.64. I don't know if that's legit or not, but and let's say that subnet doesn't exist. Well, my router would take that and say, well, I don't see 172.31.64 in my routing table, so I send it up to the 172.16 0.1, I think it is. In other words, the next upstream YC router. Well, that router sees that and says, well, this is supposed to go to 172.31 because essentially the CNT department owns everything 172.31/16. So the router upstream from us has a route in their routing table that says anything for 172.31, anything goes to that router right there. So my router was sending it upstream because it didn't have an entry for 172.31.64 dot something. That router says, well, it's a 172.31 address, so it's sending it back to my router. And it just bounced between the two until the TTL expired. If that didn't happen, if there was no TTL, those packets would still be traveling between them forever and ever and ever, well, until maybe the routers got reset, of course. But they would go and just live forever bouncing between the two routers. And I know that ITS has some routes in the 172.16 range, that's been subnetted that don't exist because I've seen some TTL expired come back when I've sent them out to the rest of the YC network. So that's an important field to keep, packets from just living forever out there on the internet. Okay, just to look at some of those fields and what their purpose is. The version obviously tells you if it's version 4 or version 6. So that's right there in the first byte, actually 4 bits of the header. So I guess they expect that IP will never be greater than version 15, since there's only 4 bits to represent it. So that might be a problem down the road for them if they maybe many years down the road. You see, we've gone from version 4 to version 6 in about 60, yeah, I'd say around 60 some years, 55 years, something like that. So it's not, the versions aren't moving along really quickly. So I guess it'll be a while. All right, differentiated services, that's after the header length, which basically says how long this header is. So differentiated services byte or bits, which is basically used for quality of service, so that packets can be prioritized and be moved to the front of the routing queue. Okay, so remember, we're talking packet headers, so switches won't deal with this at all because they don't look at the packet header. Only routers will consider things like the differentiated services field. Checksum. So again, the header checksum, is only used to protect the header. Okay, so if the data is corrupted, IP doesn't know about it. Okay, that's really up to the data link layer to determine that. So if it somehow gets corrupted, in the router itself, then you could end up with corrupt data, because this is only going to make sure that the header wasn't changed in transit somehow. And then we have the TTL, which we talked about. The protocol just says, okay, what type of IP packet is this? Is this ICMP? Is this a UDP? Is the upper layer UDP, or is it TCP? It could also be other, like a routing protocol, like RIP, or OSPF, or something like that. So the protocol field basically says what's above, what are the upper layers above me. And ICMP isn't technically shown as a layer above, but if you ever looked at ICMP and Wireshark, it sure as heck looks like it's an encapsulation of IP, or the IP encapsulates ICMP, I should say. But it's not considered a transport layer protocol, even though it kind of looks like that. And then the source and destination address. Okay. So we know some of the limitations of IPv4 addresses. Lack of end-to-end connectivity. Again, that talks about NAT. There's almost no communication directly between two devices on the internet. A host, like a client device, and a server, because just about every situation is using a private IP address for the host device. And in order to go out on the internet, it's got to be translated to a public address. So there is no end-to-end connectivity, which means you can't really guarantee that you can't identify truly who you're talking to. And that could be a potential security problem. Certain applications may require that. I remember when we first were getting internet connectivity up in this college I used to work for, the library bought some application to look stuff up, and it required end-to-end connectivity. So we actually had to assign public IP addresses to like 2 or 3 workstations inside the library, or else it wouldn't work. Now, I'm sure that's been rectified, because that's not a smart thing to do with IPv4 because of its lack of security. But certain applications will work better, will be more, it seems almost, the opposite, but will end up being more secure with IPv6 because you have end-to-end connectivity, and you can truly identify who where a packet came from. Any packet that comes from Yavapai College is going to be translated to a 198, what is it? 198, 161, can't remember now. But there's, just a few public addresses that all communications from Yavapai College will be translated to. So if somebody was doing something nefarious inside the college, it would be difficult, not impossible, but more difficult to find out who is doing that. Now you can check the NAT tables on the routers, but that depends on timeliness because NAT tables don't sit there forever. If there's no communication from a particular device out to the internet, after a certain period of time, the NAT table entry gets deleted. So with IPv6, you'll see the source address. It'll be a public IPv6 address, and it'll be easier to track down who sent it. Okay. All right. So anyway, NAT, while it was necessary for IPv4 to continue working, let everybody use private IP addresses so that not every device had to have a public address in the world because it wouldn't work because there's not enough. A lot of problems with it. Slower for one thing, but it increases troubleshooting and has potential security problems. Conversely, it also increases security for the internal hosts, but we'll talk about that a little bit later with IPv6. Okay, so IETF is the organization that develops these protocols, and these are all the three biggies anyway of what IPv6 brings to the table. And this is the number of addresses, 10 to the 36 approximately. So lots and lots of zeros. So IPv4 is, just 4 times this, 4 billion. So lots of extra zeros compared to IPv4. Okay, eliminates the need for NAT. So as you can see, many fewer fields in the IPv6 header. You have to have the version, of course. The traffic class, it replaces the DSC field. In other words, the quality of service field. It's a little bit, it actually ends up being 8 bits instead of 4. So it's a little bit more complex than what was in IPv4. Flow header, or the flow label. The flow label is something that will eliminate, let's say, make it easier for the transport layer, because the flow label can guarantee that all packets from the same conversation go out the same port, same router port. So if you have a time-sensitive application, for example, voice or video, then the flow label can ensure that the packets all go out the same interface, because the internet's going to have fault tolerance. It might have 2, 3, 4 or more routes to get to the end network. Well, and it might by default round robin between those just to keep the ports loaded about the same. Or it might go out a certain port based on how busy the upstream router is. So that can cause issues where in a large transaction of thousands of packets, some packets go out one direction, some go out another, and they arrive out of order. Well, flow label will prevent that from happening. So the TCP on the other side doesn't have to reassemble them, or better, you may not have to use TCP. You could use UDP, which is much more streamlined than TCP. And since UDP can't reassemble packets in the correct order, but it's faster, UDP makes a good option for certain things like voice and video, because that flow label makes it so that TCP isn't quite as necessary as it would be with IPv4. All right, the payload length just says how big is the data inside this packet. Next header field. So this is what they did with IPv6. This next header field allows IPv6 to, well, let's say normally this will point to the transport layer header, but you can extend the functionality of IPv6 by adding headers to it, and that next header will point to the next IPv6 header. And that way you can get additional capabilities without having to do things like additional encapsulations for security, encryption, things like that. But normally it's going to point to the transport layer header. Hop limit is the same as what in IPv4?
TTL.
TTL. And that makes better, that actually describes it better, because routers decrement the TTL. As soon as they get a packet, they decrement the TTL before they actually do anything else with the packet. Because if that TTL goes to 0 after they decrement it, then it gets tossed. It basically says, well, this packet expired, and some routers will send a message back to the source saying your packet expired. It'll say TTL expired. Well, so hop limit makes, is more better descriptive. Now, TTL, there is actually some time involved, a time factor with TTL, and it goes back to, again, with IPv4 and fragmented packets. So what a router will do, if packets have been fragmented, there'll be an indication in the header. It'll have a, some sort of bit set that this is a fragmented packet. And the router will sit there and wait for the other packets, or the other fragments, I should say, to arrive before sending it off to its destination, if it can. If the MTU is such that it can reassemble the packet and send it out as a bigger packet. Well, the problem is that what does it do if those fragments sit in its buffers and the fragments that are missing never arrive? It's got to have some way to know when to give up, essentially. And so that TTL, time to live, the router starts a timer, and every tick, whatever that is, I don't know if it's seconds or fractions of seconds, but whatever that time period is, it goes and decrements the TTL while it's sitting there in its buffers. And if the TTL in the fragments goes to 0, then it says, all right, I give up. I'm not waiting anymore for the rest of this bigger packet. So time did play a part a little bit in IPv4. In IPv6, there's no fragmentation, so making it hop limit makes a lot of good sense. And again, the header checksum is removed. Fragment offset is removed because there is no fragment. The flags field were removed because there's less stuff to flag in IPv6. Like, one of the flag options was the do not fragment bit. And if that bit was set in the flags field, then that means that routers or any other device could not fragment the packet before it went on to its destination. All right, so we pretty much covered all these, I believe. Yeah. So 16-bit field on the payload. So that basically limits our packet size, our total, payload size, what's inside the packet, to 65,000 bytes. So that's probably pretty reasonable. So I think we covered all this. The next header, again, will point to what, the header of the next upper layer protocol. Or if it's an encapsulation of some sort, like you could say ICMP is more of an encapsulation than a upper layer protocol. Anyway, the next header points to it. All right, so extension headers, like I mentioned, are optional, and they can provide additional stuff on what to do with the IPv6 header. If for some reason you really need fragmentation, you could build that in with an additional header, but it would be unlikely. But other things are like mobility support, to support mobile devices when they get handed off from one, whether access point or a cell tower or something like that. Security could be part of the next header, whatever. So they pretty much accounted for, making IPv6 flexible by adding these additional headers. So there'll just be additional headers. There'll be an extension header. So, and these will have some information on whatever the extension is supposed to, whatever functionality the extension is supposed to have. All right. Yeah, so like I said, normally it just points to the upper layer header, but if it has extensions, it points to another header inside inside IPv6's packet header. All right, hosts and routing. Let's take a break now. It's about 11, 12 minutes to 7, so let's resume at 7. About 12 minutes, 11, 12 minutes. Professor.
Hey man, how you doing? Good? Hanging in. Yeah.
So busy, it's not even funny.
Some people find that, planning on, some people find busy good.
Busy, well,
But it-
yes, but except for now, there's one where the shop.
There was, yeah, depending on each.
Time I get at this point in the night.
Right. Literally just. Thankfully, you have a badass part.
This is true. She basically did.
Where?
But I, interesting one, actually.
What?
Well, she gets slammed. She's a teacher.
Yeah.
No. Oh, yeah, okay, well, yeah, just keep me apprised.
Thanks. Well, you guys are both badasses.
It's pretty, so I mean, and the one thing that is at least as good for me is I'm finding it interesting.
That's
It really is. It's interesting. It's like, oh, it's figure it out.
I was just curious. Wow, all this is good.
Because if it wasn't interesting, it was like,
How's your business got C pop up?
It's gonna be more of an exhausting grind.
Oh, you see,
At least if you can.
Yeah.
Yeah,
I was sort of surprised because it's been going on and on.
we, so the spanning tree is part of
Yeah.
switches functionality.
So we're.
It
we're hanging in.
basically
It's just, the time to.
make
do
sure
so
that there's
from
not a switching loop. That
physical demand
the
of-
switch is connected in a loop that could cause broadcast
Usually,
one.
by the time 9 o'clock rolls around.
And
Yeah.
I actually thought that we had all
Part of
the
that's
ports
for
on
me.
the switches
like populate it.
spanning tree turned off
Yeah.
because
So
what you typically want to do is if you know that
it's just.
certain ports
It
are
is.
always going to be connected to
But
hosts
we're,
and
all in
devices,
all, we're doing pretty good.
then
Good,
there's
man.
a command to turn spanning tree off so that there's no need for it, right? You're a host, you're not going to create a switching. But it must be that there's some ports that are not. Well, let's see, STP, I believe, is a multicast, so it's probably, if there's any ports that are using it, maybe going out to all ports. But anyway, I have to look at the configuration because so what spanning tree does when a switch first gets connected to something, probably saw it took a while before the switches would actually accept data, right? You plug them in and they would go amber, and then it would take several seconds for them to go green. Part of what that delay is spanning tree sending out packets to make sure that what just connected to it isn't a switch that's causing a loop. And then once it figures out, okay, I'm not getting any replies because hosts don't send back spanning tree packets, then it says, okay, I guess we're good to link, to connect. But temporarily it puts the port in what's called blocking mode so that packets don't get forwarded that could end up being a loop. And then once it decides that there is no loop, what's connected here isn't causing a loop, then it then it links. And then periodically it just sends out kind of status or packets to make sure that the topology hasn't changed. So that's what happens, so that that's why you're seeing packets.
So many.
And so
STPs.
Cisco, which is the switch that we've got up there, is the culprit sending that spanning.
Gotcha.
No other devices, no other, none of the computers will send out spanning trees. So anything that spanning tree should be coming from our switch.
Gotcha.
Stage. Then one.
Alright, yeah, my back just keeps going out randomly,
Did you hear it?
like 2 years ago.
She had the surgery to get a disc shaved off. That was one thing that
Yeah, I may have to have surgery with some.
but back pain, that's. I've been very fortunate. All the heavy stuff that I've been lifting in my life. I've never.
I was
A few small.
110
on
on
that.
It sucks not being able to move.
So you work smarter, not harder.
That's why I'm here.
I'm still like, I don't know. It's like, kind of like yours.
I didn't show it. That was like.
I kind of was just hoping that, like, like you said, there was gonna be class and like he's pulled the rug from under us. And it's just, well, hopefully it can be, just
How you doing, sweet?
timing, whatever direction, it's still doesn't work.
Like 2 different times, 2 or 3 different times, like nodding off and
That's why I'm doing this.
catch myself. There was a way to, there was a way to save it and send it. I would like do a packet tracer or something. Like, save it and send it.
You
on
can
this
save it
drive.
on here and then
Progress.
separate it.
I feel like Windows should have been like. on its
He
own
said that
files.
the reason he likes us to log in with a specific class,
Just get away with that.
he said that we can see things on the computer.
Well, right, but if I was gonna do something and I wanted to keep it, I wouldn't be able
Yeah.
to
Yes,
now.
that is true.
Too much. Hopefully.
And then I guess the other thing too is I'm still trying to kind of pay attention. And if I was doing packet tracer, and I'm totally staring at the screen and I'm paying attention.
She automatically just did it through passing the classes.
So I'm gonna try and hang out.
Just use the F button.
It's not just. See.
I feel like after you go through the certification program, it's good. It's a strengths here.
No, they. So.
Really do it.
We might take that. Second.
You didn't see my Facebook yet, did you?
No.
This must start a job.
Oh. Oh, that's pretty good.
It's funny, huh?
Yeah.
All right.
I'm gonna show that to my class tomorrow.
Yeah, you should.
Yeah.
It's pretty
Marnie, you got my response to your why.
I got it. Yeah, thank
So
you.
what, there's a setting on the
Thermometer test.
on the grade book that if you can automatically assign a 0 if something was turned in late. And apparently that was checked. So a lot of people were on the same boat. So I just changed the setting, and it's unfortunately changing the setting doesn't automatically, so I had to go in manually, get rid of the 0 for people that had turned it in somewhat late. And I wasn't counting off yet for late assignments.
In the syllabus, it said that if we turn things in, we can still turn things in late, but there's a deduction. What's the deduction?
Usually after the first week, it's 10%, and then each full week late after that, an
So
additional 10%.
There's a grace period after the due date,
Yeah,
like.
Grace period, to be honest, and most people make out because of this, is the grace period is either 1 week or until I get around to grading it. So if you turn it in before I get around to grading it, even if you're 2 weeks late, I don't take off, because if I'm gonna be that late, then I should give a little grace to the students if they're a little bit late. But I do plan on catching up on my grading, so don't expect that you can turn something in from week 1 a week from now, or actually 3. I think I'm through week 3, 4, and not get taken off. But yeah, until
When I got late was like less than an hour. It was just after midnight that I turned it in.
yeah. Well, to Canvas, it's a second after midnight.
I understand.
And what it is
Based
I
on what you're
usually.
saying, then when you grade it, it won't really be marked down because it was
Yeah.
so close to the
Yeah.
due time.
What I usually do is when we're getting towards the end of the class, like to week 7, then I do set that option, and it will set all assignments that have not been turned in, not late, but not been turned in, to 0. So then I don't, because people, if people look at what their current percentage is, by default, it's only calculating stuff that they've turned in, until I turn that option on to say, put 0s on the stuff that they haven't. And now their grade goes from 90 to 40 if they haven't turned in a lot. So, but I let people know that, that don't be fooled by your percentage. All those missing places in the grade book will be taken into account when I actually go to grade things. Okay, looks like I need to get moving. Okay, host forwarding decisions. So believe it or not, hosts have routing tables too. And you can see that in command prompt by doing a route print. There's actually a couple of commands, I think. There's a config option too. Route print is the one I use. So this is a routing table on a Windows machine. It's pretty, there's a lot of stuff in there that mostly we don't care about. But basically, to make things easy for a computer to decide what to do when it has a packet to send, every single possible option of addresses is taken into account, and where it should go. And that way, the decision tree for a host is look up in your routing table if it's going to 192.168.175.0 network. Well, that's on link, meaning that there is a physical NIC that has that belongs to that network, and the interface address of that NIC is is 175.1. So most of this is just things like, you know, the actual networks that are represented by the network interfaces. Now, this has a bunch of network interfaces, even though there's not several physical NICs because of virtualization. When VMware is installed, it creates a bunch of virtual network interfaces that have IP addresses that VMware assigns. Okay, so that's what all those extra addresses are. On your machine, your laptop, if you don't have virtualization, like VMware or what's the other one that most people use, the open source one, VirtualBox. If you don't have something like that installed, then you know your routing table will be much simpler looking. It'll have these addresses, and then it'll have, you know, the broadcast ones, but it won't, and then it'll have an address for your NIC, but it won't have all the extra ones. It'll have the 224s though as well, which are multicasts. So if you notice, what does this computer do with multicasts? 224.0.0.0 with a 240.0.0.0 subnet mask. That basically says any address from 224 to 239 in the first octet will be sent to every address. In other words, it treats it like a broadcast, sends out every network interface. Because that's what multicasts, you know, what most devices, how they treat multicast, they treat them essentially like a broadcast. So anyway, there's your routing table. Now that first entry, the 000 entry is, the first entry is the default route. So that will have as the gateway will be the router that your computer should send packets to when it's got a packet for a remote network. And it'll have, you know, the IP address of your NIC. All right, and then the metric is just I'm not really sure how Windows calculates the metric anymore. I used to, but they've changed it over the years. It used to be a much simpler metric, you know, like 1 and 5 and 10. I don't know what they do now exactly, but the metric is basically when there's two ways to get somewhere, the lower number metric wins. So like on my computer in my office, I've got 2 physical NICs. So potentially I could have, well, by default, I have 2 default gateways. I changed that. I used the route command to delete one of them. But before I made the change, when you did a route print, you would see 2 entries for 0000, one for the one NIC and the other for the other NIC. And the metric would determine which one would get the traffic.
So basically the metric is saying it's faster.
Yes.
It's
The
just a
lower the
faster-
number, the
it's
quote,
faster route.
faster. Yeah. You know, it's basically, they use the term distance. It's not a distance that's measured in, you know, feet. It's the distance is usually measured in either hops, number of router hops to get to the destination, or in some cases, the speed, the bandwidth of the links of all the hops to get to the destination. So it depends on the routing protocol that's being used as to what the metric is composed of. In any case, so you know, your host machines, Windows and Linux, same way, has a routing table. It doesn't mean that they're routers. My machine will not route packets. If I send packets to my machine that are supposed to go to some other network, my computer's not going to deal with it like a router would. But they just have a routing table so they know what to do with a packet originating from the computer. So when somebody creates a packet with an application, then one of three destinations will be determined. Either it's a 127 address, and that 001, remember, can be 127 anything. It's not just 001. The second, third, and fourth octets can be anything except all zeros or all 255s, and it'll still be the local loopback. 127.001 is just what's used by tradition. And then ::1 in IPv6. Now that is the only loopback address for IPv6, ::1. And the colons, you know, just means a bunch of zeros. So it's basically 15 fields of zeros followed by a 1. And then, so itself, so if you ping yourself, then that will be the destination. A local host means that you're communicating with a device on the same IP subnet as you are on. And then the device knows, okay, I need just to get the MAC address so I can deliver it to that device. So I do an ARP, or check my ARP table first. If it's not there, do an ARP. Or it can be a remote host, which means it's on a different subnet. And if it's on a different subnet, where does it send the packet? My computer wants to ping 172.16 dot something. Where will my computer send that packet or that frame, let's say? Default gateway, yes, to send it to my router, which is 172.31.208.250. So those are the three possibilities, and it determines where to send them by looking up the looking in the routing table and seeing what the routing table says to do. So it doesn't really have to do much calculating or thinking for each packet. It just looks in the routing table, and the routing table has it covered. There was entries for 127. There was entries for all the local networks for each NIC in the device. And there's the remote hosts are all represented by the zeros network. That's the default gateway. All right, so how does the device know if the IP address that it's trying to send a packet to is on the same network or a remote network? How does it know?
Subnet mask.
Subnet mask, exactly. It does so if this is the address of the something different. So this is my destination. And the people on, I keep forgetting people on Zoom can't see this, so sorry. Let me bring up the whiteboard. I'll figure it out by the time the class is over. Okay, so if my destination is 172.31.210.1 and my NIC is 172.31.209.100. So based on that information, should my computer send this packet with that destination? Should it do an ARP and get the MAC address and then just send it onto the local wire, or should it send it to its default gateway?
How do we tell?
Yeah, you can't tell. Exactly. It was a trick question. Oh, did you say, how do you tell?
Yeah,
Yeah. Well, you don't. You can't tell. So it was somewhat of a.
Is that assuming it's class B or?
Right, you have to know what my subnet mask is, right? Okay, and
Once the mask for that would be. Maybe if I can find it. 255.255.0.0, right?
well, that's what it would be if we were in a world that required you to use a classful subnet mask. But we don't, I can put any subnet mask I want on my machine, and my address is, this is the one, this is my physical NIC. So that's not quite 255.255.0.0, 255.255.248.0, which I'll just tell you, well, if you did that, that one table, that one subnetting table, and knew how to do it, thing that you want to find out is 172.231.209.100 in the same subnet or different subnet than 172.231.210.1. And I can tell you right now, they are in the same subnet. That 248 basically means that the subnet that my computer is in, 172.31.209.100, is the 172.31.208.0 subnet. And that subnet goes all the way from 172.31.208.0 to 172.31.215. Actually, yeah, 215.254. So 210.1 is within that range. So in this case, because this subnet mask basically, like I said, it makes the subnet go from, with the 248 subnet mask, my subnet, that my computer is in the 172.31.208.0 slash, and the 248 gives me 16 to 21 bits slash 21. And that goes to 172.31.215.2. Well, the entire address space goes to 255. So that is with a slash 21, that's the address space. So these two guys are in the same subnet. So he would do an ARP on the 210.1 address, looking for a MAC address. Now, if I change that destination to, 216.1, now, when my computer does the binary AND with 255.255.248.0, he will get 172.31.208.0. That's the network ID. And he would see that he would apply the same subnet mask. He would do the same binary AND with 172.31.216. And he would find that this is in a separate subnet that's in the 172.31.216.0 subnet. And so since they wouldn't be in the same place, the same subnet, then he knows, okay, I got to send this to my default gateway. Okay, so that's what for every, and it's not for every packet. The computer doesn't, if somebody's transferring a file to a server, then basically does it once and says, okay, this whole stream of 5,000 packets or whatever it's going to end up being, is gonna go to whatever, either the local LAN or to my default gateway. He doesn't have to do the calculation for every single packet, but for every stream of packets that are going to the same place, it'll do that. It'll do that calculation. Okay, so that's how it knows. It's got to do the math. It's got to do the binary ANDing of its own address with the subnet mask. Now, chances are Windows has already done that for its own address. So it's got a place somewhere in the registry that's probably in RAM for what its network ID is. Because there's no sense in it having to do that calculation over and over. It'll only have to do it any time the IP address changes or every time the machine is restarted, which could also cause an IP address change. So it's got that somewhere stored in memory, but for the outgoing, the destination address, it has to do that for every stream of packets it's going to be sending. And it does the binary AND with the subnet, with its own subnet mask, because it doesn't know the subnet mask of the destination address. So the best it can do is use its own subnet mask, do the calculation, and if the two results are the same, they're on the same LAN. If they're different, then they are, then it's a remote device. All right. Okay, an IPv6, more or less the same thing. They just call it different. It's a prefix, but you're still, the prefix just says, look at the first however many bits. And in IPv6, it's much simpler because unless you are really looking to make your life complicated, the first 64 bits of any host will be the network ID, and the last 64 bits will be the host ID. So there's no, from a human standpoint, we don't have to figure that out because we shouldn't have to. Like I said, it's within the standard to allow deviation from that, but you shouldn't, because there's no reason to not use 64 bits for the network ID, 64 bits for the host. Okay, so we know what default gateway would be our router or our layer 3 switch, which is really just a switch with a router built in or router capabilities built in. So it's called a layer 3 switch. So if you don't have a default gateway configured, now depending on the operating system, Windows will just say something like transmit error or something. Basically, if it knows it has to send the packet to an intermediate device to get it to its destination, and there's no default gateway configured, then it gives you some sort of weird error like transmit error. Other operating systems, it is within the spec for a device to basically send out a broadcast, send out a broadcast looking for a default gateway. But you don't see that very often. So in most cases, if you haven't specifically configured one, then you'll get an error if you've got remote traffic. All right, so just like any other destination, the host will need the MAC address of the default gateway. So before the first packets that are ever routed, or the first packets that a computer needs to send that will go through a router, he's got to first ARP for the MAC address of his default gateway. And then, depending on what the computer is doing, that's probably an address that gets kept in ARP cache for a pretty long time because a lot of communication goes through the default gateway. Yeah, so, and again, whatever you plug into the default gateway in your IP settings, so when you are looking at so when you're looking at your IP, your settings of your network interface, whatever this address is will show up in your routing table as the 0000000 route. So that, and if you happen to have two NICs and you've configured two default gateways, which Windows will warn you that that's not a good configuration, but if you did, then you'll see two entries for the 00 network. So just look at that again. Okay, so 208.250, that matches my default gateway. Right there. So now what else is that route good for, that route command? You can also create routes, delete routes. When you only have one NIC, physical NIC, most likely you don't need to do anything with the route command other than if you want to look at your routing table for some reason. But if you have two NICs, like I have in my machine, one NIC is connected to the 172.31 network. The other NIC is connected to a port, a VLAN on that switch that goes out to our secondary internet provider, Sparklight, which is not firewalled to the teeth. So when I need to like access Kali Linux or other prohibited by college sites, I basically get the IP address of whatever site I want to go to, and I do a route command, route add, and then, you know, the IP address and the mask, whatever it happens to be. And then I say, go out my secondary, this isn't the right address, at least I don't think it is, but this would be the right command. Route add my destination. Now, I didn't actually need to put the .23 there. I should have put .0 because the subnet mask will just mask off the 23 anyway. So anything destined for 11.23.1.0 will go out to that. Actually, what I would want to put is the router address of the Sparklight connection. So if this is Kali Linux, for example, 111.23.1.23, then with that route command, it would make sure that any packets going destined for the Kali Linux website would go out the alternate internet provider, so it doesn't get firewalled. So that's what, you know, one purpose and one reason you might have two NICs. One is for most communication, the other is, you know, occasional communication to a different provider or different router or whatever. That's usually the most common reason to have two NICs. Okay, so some of you that are in classes, that some of the cybersecurity classes that where you have to access Kali Linux to do things like update your Kali installation. In Kali Linux, we have to change it periodically, but there's a router in our VLab that has a connection to our Sparklight internet provider as well. And so we set it up so that any of the virtual machines in these classes that need to access Kali Linux will go through, they get routed out the Sparklight connection. Otherwise, you would get blocked. And occasionally, the address that we're using changes, and somebody's got to let us know you're not accessing Kali anymore, and we have to go in and change the router and add a different route so that it routes appropriately to Kali Linux when needed. And there's other sites. There's a few other things where we route out the alternate internet provider. Okay. So I already talked about the host routing table. I don't think there's more that needs to be said about that. When you see on link, that just means that there's a network interface, whether physical or virtual, that applies to that destination. Okay, packet forwarding decisions. So routers obviously have routing tables. And so typical routing table, there's more fields than just this, but it's, this is left out of several fields that are in between here. Doesn't matter too much because these are the ones we care about. The destination network, in this case, 10.110/24, and then where do I go to get to that? So in this case, it's been simplified to just say via router 2, via R2. In reality, it would have the IP address of router 2. The actual routing table would have router 2's, this 209.165.200.226 would be here. This is just to simplify it. And of course, there'll be a default route listed as well. Well, not by default, somebody's got to create the default route. So Cisco routers, they have nothing in their routing table when you first turn them on. If they don't have any configuration file, then there's nothing in the routing table. Every interface that you configure, that you give an IP address to and enable by doing the no shutdown command, that interface will be entered into the routing table as one of the routes that router can get to. Any other routes that end up in that routing table have to come through either an administrator creating a route using the command line, something similar to like what I showed you with Windows. It's different syntax, obviously, but you can manually create a route, which is what you typically do to get the default route, or you use routing protocols to let the routers learn from each other, what all networks they know about. Okay, so when a router receives a frame from a device, so in this case, PC1 is communicating with PC2. So the packet, PC1 will take the frame, get the MAC address of router 1, and send it to router 1 to be routed. Router 1 looks up in his routing table, okay, 10.1.2.10 or 10.1.2.0 network. And so this is totally the wrong. One of these two is wrong. Either this needs to be 10.1.2 or that needs to be 10.1.1. I'm not sure which, but it's clearly wrong. Otherwise, it wouldn't work. So let's take this as an example. And it looks like this is what's wrong because they've got 10.1.1 in multiple places, 3 places, only 10.1.2 in one place. So that's just a typo. That should say 10.1.1, 0/24. But let's say it was 10.1.2. If it was, and router 1 goes and looks at his routing table, and this is what he finds in his routing table, he would basically say, oh, can't get there, and throw the packet out. Now, he does have a default route. So in that case, since he does have a default route, he wouldn't throw the packet out and he would still send it along. Well, this is router one's routing table. He would send it along to router two. But router two, not knowing about the 10.1.2 network, if this was his routing table, would just toss it. So, yeah, they really, so yeah, 10.1, yeah. So this needs to be 10.1.1, not 2. Should try to fix the slide. I'm not going to right now. Okay, so we pretty much already talked about this. This is directly connected, remote or default. So this is a little bit different than the host. With the host, it was either loop back on local LAN or remote. In this case, the default route might, basically you can have a bunch of remote networks in a routing table, but you're not going to have every remote network on the internet in your routing table, right? So routers on the internet, they might have routing tables with thousands of entries, but eventually, that still doesn't take into account the whole internet. The whole internet is hundreds of thousands, really probably millions of networks. So no one router has every internet route in it. They will all have some default route that says, if you can't find the route in this routing table, then send it, upstream to one of these other routers. If you don't have a default route in your router, then anything that doesn't match a route in the routing table gets tossed by the router. He might send back to the sending host network unreachable, an ICMP network unreachable message. It all depends on whether the router is configured to do that or not. By default, I think they will send that, but a lot of people configure their routers to not send those extra ICMP messages. All right, so static routing. Static routing is just what it sounds like. It's a route that's manually entered, just like static IP addresses are manually entered by somebody into the configuration of the NIC. Routes are manually entered by the router administrator. And it's the same syntax pretty much that I showed you with the route add command on a PC, except it's IP route in global config mode. The first argument is the destination network, followed by the subnet mask. On Windows with the route command, you have to use the keyword mask in between there, but on routers you don't. So IP route command doesn't use any additional keywords. So destination network, subnet mask for that destination network, and then the next hop. Okay. So the next hop being the IP address of the upstream router that can get to that 10.1.1.0 network. Okay, so if you don't run a routing protocol where the routers exchange information, then you need to, in a situation like this, you would need to create a route on router 1 on how to get to the 10.1.1.0 network. And on router 2, you would need to create a route on how to get to the 192.168.10 network. Because doing just one doesn't help. The packet, if you just do this on router 1, the packet will get to router 2 and actually get to PC2. PC2 will send the reply, but router 2 won't know how to get to 192.168.10 unless you've got another static route configured on router 2 to say, go to 220.225 to get to that 10.0 network. Okay, so in a situation like this where there's multiple ways to get to the destination. So you've got 3 routers configured in a triangle. So the default, if the main route is to go from router 1 to router 2 to get to the 10.1.2 network, then what happens if the link goes down, you need to have a secondary static route that says if the first route fails, go to router 3 to get to that network. So when you've got fault tolerance, redundancy, it's a pain to have to use static routes because that means you've got to configure a static route for, all the possible route directions that the packet can take. And you also have to depend on when the links are fixed, right? So if this link goes down between router 1 and router 2, well, that's presumably the fastest way to get to the 10.1.2 network. Let's say it's a gigabit link. This is maybe a gigabit or maybe 100 megabit link. So this is definitely the fastest way. Well, if this route goes down, then you want a route to make sure you can still get there by going through R3. Well, what happens when this guy comes up? When that guy comes up, now you gotta, go and let the router know that that route came back up. So in any case, that can be problematic. There's also other things besides the number of hops or the speed. There's other factors that can contribute to what route is best. If you're using a simple routing protocol like RIP, then this may or may not be the best route. If this was a 10 megabit link and this was a gigabit, then it would be faster to go through 2 routers if these were faster links than that one. So that's why routing protocols, you choose the right routing protocol, and they're something you should typically use when you've got redundancy. When you have multiple paths, then use a routing protocol if you can. All right, dynamic routing is basically what it sounds like. The routes are dynamically created in the router, and that's by using a routing protocol. So the routers talk to each other and they give each other information about the networks they know, and they insert them into the routing tables. So router 2 knows about the 10.1.2 network and whatever this network is. So router 2 is going to tell router 1, hey, I know about the 10.1.2 network and whatever this network is. And router 1 will tell router 3 and router 2, hey, I know about the 192.168.10 network. And it'll tell both of them. They'll add those to the routing, that to the routing table. Router 3 will tell router 1 and router 2. Really, router 3 will only tell router 2 about this network, and router 2 will tell router 3 about this network. Oh, and that network. So that's basically what's nice about a routing table is that you don't have to go in and create a bunch of static routes. And if your network changes, the routing protocol will take care of adapting to the change. Okay, so that's dynamic routing. Things like RIP, OSPF, EIGRP are routing protocols. So the IPv4 routing table on Cisco routers looks like this. So with show IP route, you'll get that listing. If you haven't configured or enabled any of your interfaces, then you will get a blank routing table. But the top of this is just the key, what all the abbreviations here mean. So the S means static. The O means that that the route was learned through OSPF. The C means that it's directly connected. One of the interfaces has that network address, and that's the IP address of the local interface. So the C and the L's basically mean the same thing. The C is just the network ID for the interface. And the L is the actual IP address of the interface. And it uses a /32 just to say that this isn't a different network. This is actually the host. So /32, when it's used, means that this is a host address, not a subnet address. Okay, so this is what they look like. They're a little bit, ugly looking, these routing tables, but so we'll look at the first entry is the static route that an administrator created, which is the default gateway. So he gets there, he gets to any network, the 000/0 network means any network that's not in the routing table. So any network that's not in the routing table, I'm going to send those packets to .226, which is router 2, which is out my gigabit 001 interface. This is router 1's routing table. And then it says, okay, the 10 network is subnetted. There's one subnet. And it knows that it's subnetted because it's not the classical network. If it was a /8, then it wouldn't say this, but it knows that it's not the classical, so it's been subnetted. And there's one subnet, and it was learned through OSPF. So router 2 is the one that knows about the 10. Yeah, they got it wrong here again too. It should be 10.11. So router 2 knows about the 10.11 network. Both of these guys must be running OSPF in order for OSPF to be where the route came from. And router 2 told router 1 about the 10.11 network. And again, typo, that should say 10.11. And then these are just the directly connected networks, the 10.0 and the 200.224 network are directly connected, and the L's are just the IP address of the interface. Okay, so that's pretty much it. Most of the stuff that you'll see in routing, in a routing table, depending on the routing protocol, you'll see O if it's OSPF, R if it's RIP, D if it's EIGRP. Some of these others we get talked about in third class. So, okay, so that's it for the basics of the routing table. You do need to be able, for CCNA exam, and you do need to be able to read a routing table and understand, where a host could or could not get to based on the topology and the routing table. All right, that's took longer than I thought to get through that one. I forgot that it had all that routing stuff. So yeah, I think what we'll do, we're gonna have to keep you a little bit later today than usual. Probably won't get through all of 9, but I think we need to start it so that we have time on Wednesday to get that lab done. Does anyone need to take a break? It was only about 15 minutes ago that we did the last break. If you do, just go ahead. Because I'd rather not take a break and just get through at least a good part of this and have less to do on Wednesday. This is address resolution is actually we might actually get through a good part of this, if not all of it. It's a fairly short one. Address resolution, mostly talking here, since we're talking layer 3 or the network layer, about ARP and its cousin in IPv6 neighbor discovery. And since we already know a good bit about ARP, It should be pretty quick. Okay, so we know that there's two addresses and you need the MAC address to deliver a frame on the wire to another device, or even, if it's wireless. IP address, once it gets to the destination network, is really just a verification that this packet really is, belongs to the device it was delivered to. So when you're communicating, using an application to communicate, like a web browser or ping or something like that, you typically know either the IP address or the name of the device. If you know the name of the device and not the IP address, then you have to do what kind of resolution? If you know the name but not the IP address. Nope. Not ARP.
DHCP.
DNS, domain name lookup. So if you know the name but not the IP address, first thing your computer has to do is a DNS lookup. Well, this is mostly just really going to talk about the next level, which is I know the IP address, either I got it through DNS or I used it directly in the application, but I need the MAC address. And the only way to get the MAC address, there isn't really a lookup in the same way that there's a DNS, because DNS is a centralized database. So with MAC addresses, the only way to get the MAC address is from the device that owns that MAC address. So that's where ARP comes in. It's a broadcast. I've got the IP address. I send a broadcast out. It says, who has this IP address? Send me your MAC address. And the device, if it's on the network, will reply with its MAC address. And then the frame header can be, the destination MAC can be filled out with frame header and delivered. All right, so remember that MAC address resolution has to happen at every hop. It may be stored, in ARP cache, so you may not have to do ARP. Every device doesn't necessarily have to do an ARP, but every hop, every router hop there's got to be some sort of IP address to MAC address resolution when it's sending it to the next device. So the MAC address changes at every hop. The IP address stays the same throughout the journey. With IPv6, it uses something, an ICMP type of packet, ICMP-v6 type of packet called neighbor discovery. And so it's similar to ARP, but it's not a broadcast, it's a multicast because there's no broadcast in IPv6. Okay, so this is really just going over the same stuff. Mostly what you need to know, it's used to resolve IP address to MAC address. It maintains a cache, so it doesn't have to do it continually for every packet going to that same device. And the cache does time out periodically. Yeah, and it's a broadcast. So it doesn't go through routes. Okay. Yeah, so this is just the process. Look for it in your cache first. If it's not there, look in your, do an ARP broadcast. And yeah, 15 to 45. That hadn't happened in a while. Went right to the end. Good. A lot of these are just not much. There's no information. They're just telling you there's videos about it. So again, the ARP cache expires, or entries in the ARP cache expire periodically. ARP, the commands on a router show IP ARP. On a PC, ARP-A to display, ARP-D to delete. So ARP spoofing is a way that bad actors can use the ARP protocol to impersonate other devices. Somebody, sends out an ARP, let's say for the default gateway, and a device set up on the same network says, "That's me." And basically, whoever replies first wins. Or maybe it's whoever replies last wins. I'd actually have to test that out to see. So in that case, if you were to spoof the ARP reply, then that guy, every packet he sends won't go to the router, it'll go to computer C. And if computer C is really smart, if all he wants to do is capture the data and not let the client device know, is he'll then forward the data to router. So it actually goes to where it's intended. So this guy computer A will be none the wiser that this guy's kind of like the man in the middle. He's grabbing all your packets, forwarding them to the router, so you still get your replies, not knowing that there's somebody in the middle. So certain enterprise level switches can mitigate ARP spoofing by basically the fact that it has a MAC address table and it knows where all the MAC addresses are. If this DAI, is that what it's called? Yeah, DAI is enabled on a switch, then if a ARP reply comes from a port that the switch identifies as not being where that actual MAC address it lives and it's in the LAN, then it can block it. Okay, but that's an advanced feature of a switch. Your, Walmart 1999 switch isn't going to have that capability. I'd actually have to see. I think if the K9, which is a security bundle, security package, if that's installed on the switches that we have, then they probably have DAI as an option to enable. And I actually don't know off the top of my head whether they do or not. So anyway, that is one way, spoofing the ARP reply is a way to infiltrate a network. Okay, V6, neighbor discovery, same function. It's just uses a different slightly different mechanism. Neighbor discovery is used to, take a IPv6 address and get the MAC address of that device. And it's a ICMPv6 multicast. No such thing as broadcasts. So other things that neighbor discovery can be used for besides address resolution are router discovery and other services like redirection, which redirection is just where routers can tell, a device, hey, I'm not the best router to get you to the destination, use this address instead. But the ones that are more common are address resolution, which is neighbor solicitation and neighbor advertisement. Messages, which are ICMP type V6 messages. And then router discovery. When a computer comes up, you don't need to configure a default route for ICMPv6. It can basically send out a router discovery message, which is a multicast that says, hey, if there's any routers out there, send me your address. And the routers will send them their address, their IPv6 address. Okay, so the way that neighbor solicitation, neighbor discovery works is it sends out a solicitation message with basically a IPv6 address in it, just like with IPv4. And it's a special multicast So it's basically the all nodes multicast. So it works just like a broadcast. Every node is supposed to look at this packet, since it's the all nodes multicast. And if they own that address, they'll respond with their MAC address. So it really works very similarly to ARP, except it's not. It's called something different and it's a multicast. All right, and that was it for, I thought this one was pretty quick. So we only have module 10. And let me see how long that is. So we know it should start. 31, this is just basic router configuration. That's actually good to do this first thing on Wednesday, because then that's what you're gonna do in the lab. So it's pretty quick to get this done because it goes over a review of all the stuff you already know, and then it adds going into the router interfaces and doing the router interface configuration. So nothing too new, but we'll, should go over it in probably 20 minutes or 30 minutes on Wednesday. All right, so who were the people that took second shift last time? Six. So there's 6 of you that are here. He was also 7. And I'm thinking there might be another person or 2 that's not here today that went first. So how many people here too? So 6. He was second too. So do you have any communication with them?
I don't.
You know what? I'll send out an announcement and hopefully people remember and we'll be honest about it. So yeah, since we got to go over this though, does that really allow me to say come in late? I was going to do that because I know that it's a pain to sit around. What I could probably do, yeah, I can just do the lesson twice because it's not going to be that long. So the people that had second shift come at 5:30 on Wednesday. We'll go over real quickly. It's really not that much to the additional configuration. We'll go over the additional configuration to configure a router. You'll go do it. And then the other people, if you want to, you don't have to, but if you want to come in, let's say at 6:15, 45 minutes later, then you can. I'll do the lesson again. But hopefully by that time, they'll be done and you can take the next shift. If you want to come at the regular time, be my guest. You can hear it twice, or maybe you can get in the first shift if not everybody that was in the second shift last time shows up. Okay, we'll see you Wednesday.
Well, I think the likelihood of oh, yeah, they will all be being used, huh?
Most likely, yeah.
You got a 5 out of 10 on that one without like a comment.
Yeah, it's because in the checklist, only one of them had a date. So I didn't know if you left early and didn't do both of them, or if you just forgot to put a mark down.
So is there there's 2 different places where we?
Well, one for each lab.
Yeah,
There's
so
2.
I did just one.
So what's the left?
Yeah, so it's me and it.
Yeah, so you only put down there. If you did both of them,
Okay.
then I'll change.
Yeah, because.
Kind of figured you did, but
Yeah.
I wasn't 100% sure if maybe you left early and I didn't notice.
We're gonna do them together, so I'll make sure.
Yeah, I'll fix it.
Yeah, thank you so much.